Hello, pre-calculus students. In previous lessons, we have learned some trig identities and verified trig identities. Today, we're going to use those skills and solve equations that have trig functions in them. So here's a problem from page 365 of our current textbook. Much like solving any other equation from our algebra days, we want to get our trig function isolated on one side of the equal sign. So I added sine x to both sides, added square root of 2 to both sides, and that got me to this step. Divided both sides by 2. Now I got sine x equals this. Now here's the fun part. How do you write the answer? Turns out there are 6 different ways we could write the answer. And you need to know all 6 of them. So one way, I say 3, but then I say, oh, there's actually 6 because you could write the answers in either degrees for all 3 of these or radians for all 3 of these. So one way is to give all possible answers in one revolution. So that would be 0 to 2 pi or 0 to 360 degrees. And please remember, whenever you are writing in degrees, you must put your degree symbol. If there's no symbol up there, if there's no units, it's radians. So you could give your answer just in principal values using the principal values of those arc functions. So first and fourth quadrants for sine, arcsine and arctangent, and first and second quadrants for arc cosine. Or you could give all real values of x. And I would tell you which way to put your answer in a problem. So let's go back to the problem that I gave you where we had solved for sine x equals root 2 over 2. If we're answering, let's just do this problem in radians. If I want it in one revolution, so on the unit circle, what are all in one complete revolution, what are all the values of sine? Or all the values of x that have a sine of root 2 over 2? Well, positive sine would be in the first and second quadrants. That would be pi over 4 and 3 pi over 4. If I asked you to solve this just for the principal values, well, we'd take the arc sine of this and we'd get just pi over 4. Now, if I wanted all real values, well, it would be pi over 4 and every 2 pi before and after that, and 3 pi over 4 and every 2 pi before and after that. So here are the 3 ways I could write a solution to this equation. And of course, there are 3 other ways. I could put all of these into degrees. So now again, we are combining our algebra knowledge and our trigonometry knowledge into the same problem. So here's a problem. We start solving, and when we get down to this step, when you take the square root of sine squared, some of you just want to put plus or minus over here. Do you know why you're doing that? The square root of sine squared is actually the absolute value of sine x, and then it's this number, sine x, the number inside the, the absolute value sign that could be positive or negative. So I actually skipped a step here. I could actually say positive sine x equals root 3 over 2, or negative sine x equals root 3 over 2. And that's what leads us to this step. So now, if I said, give me all answers within the first revolution, well, I have positive or negative root 3 over 2. Here they are, 1 in each quadrant. If I give principal values, here they are. And note that the answer here is not 5 pi over 3, which would be coterminal, but it's negative pi over 3, because we go from negative pi over 2 up to pi over 2. or negative 90 degrees to 90 degrees. So this would be like a negative 60 degrees. That's coterminal with, but not equal to 300 degrees. So we would not say 5 pi over 3. Principal value would be negative pi over 3. And then all real values. And I put here plus pi k, because pi over 3 plus pi gives me 4 pi over 3. 2 pi over 3 plus pi gives me 5 pi over 3. So if instead of going 2 pi, you just go every pi after this one and every pi after this one, you're going to get solutions to this equation and this equation. So again, let's take a look at this problem that we can turn into a polynomial. All we have to do is make this, I call it a Miller substitution. That's why we use the letter M. So we let M equal sine x, then we can rewrite this like so. Now we use Vieta's method to factor. Bring the negative 3 here. 2 times 1 is 2 here. What numbers integers multiply to give 2, add to give negative 3? Well, here they are. So I rewrite this, splitting up the negative 3m to negative 2m minus 1m. Find the greatest common factor in the first two terms is 2m, and I'm left with m minus 1 in the parentheses. What do I have to factor out of the next two terms to have an m minus 1 in the parentheses? Got to factor out a negative 1. All right, so now I can use the zero product property. Either m minus 1 equals 0 or 2m minus 1 equals 0. So I get m equals 1 or m equals 1/2, but this problem has no m in it. So now I have to do my substitution. So now it's either sine x equals 1 or sine x equals 1/2. And in this problem, I said, let's give our answer in degrees and in 1 revolution. So where is sine equal to 1? It's equal to 1 at 90 degrees. Where is sine equal to 1/2? Well, that would be at 30 degrees and 150 degrees. So as you can see, we're just using our algebra skills, and we're now, upping our game a little bit by throwing some trigonometry in at the same time. Now on this problem, when you see a problem like this and you have a sine x on both sides, some of you are going to want to divide both sides by sine x. This is a bad idea. Let me show you why. I'm going to rewrite, I'm just going to make a similar problem. This is going to be x squared equals 2x. If I divide both sides by x, I get x equals 2. But this is an x squared problem. There are two solutions. Where's the other one? Well, it turns out by dividing both sides by x, we rule out the possibility that x could equal 0. And in this case, x equals 0 works. You can't do it like this. You bring the 2x to the other side, factor, then use the zero product property. And by doing that, you get both of your answers. So we don't divide both sides by anything. We bring everything to one side and we factor. So I bring the 2 sine x to the left side of the equal sign, factor a sine x out. Now using the zero product property, either sine x equals 0 or the sine of x minus 2 equals 0. Well, where does sine x equal 0? Well, if we're doing 1 revolution, well, actually, this would be all real solutions here. 0 and pi in one revolution, or you could just say pi times n, because this would be all real solutions in radian form. So as long as n is an integer, the sine of pi times n will be 0. Over here, we get sine of x equals 2. Well, we know the sine of x is never greater than 1, so there's no solution to this one. So our answer is here. In one revolution, this is our answer. In principal values, the answer is just x equals 0. And all real values would be x equals pi times n. All right, you're probably thinking, man, that's really easy. I can do this. Miller should just end this video now so I can get to work. Oh, wait, what? We have two different trig functions in this one? Okay, you don't shut the video off yet. So we have a secant squared and a tangent squared function in this one. Well, you know, that's going to be kind of weird. So we have to start going back to a couple lessons ago. Is there anything we can substitute in here to make everything the same? And sure enough, secant squared x is tangent squared x plus 1. That's one of our Pythagorean identities. Now you see that everything's in terms of tangent x. That makes life much easier. So tangent squared x equals 1. Now, I've said I didn't say, I'm going to show you a couple of ways you could do this. You could say tangent squared x equals 1, or you can factor this, because this is a squared minus, that's a b squared, that's 1 squared. So you can factor that to tangent x plus 1 to tangent x minus 1 equals 0. We're just going to do this way first. So if tangent squared x equals 1, the absolute value of tangent x equals the square root of 1, or 1. So tangent x could be positive or negative 1. And where does that happen? That happens at pi over 4 or 45 degrees, 5 pi over 4 or 45 degrees. These are all the answers within one revolution. If you come up to this way of doing it, then you have tangent x equals negative 1, or this equals 0, which means tangent x equals positive 1. You're right back to this step here, and you get these same answers. So this one became a lot easier once we did a substitution to make sure everything was in terms of tangent x. Last slide. Okay, so now I have the sine of 2t. Oh, well, that's fun. That throws a little wrinkle into it, doesn't it? So we're going to solve for the sine of 2t. And how are we going to solve this? Well, we know that, if we look at all real values, if we take the arc sine, 2t is going to be pi over 3, and every 2 pi k, or every 2 pi after that, or 2 pi over 3, and every 2 pi before and after that. Solve for t. Here are all real answers for t. Now, based on this, we could determine what values of t would work within one revolution, or we could figure out what values would work if we just did the principal values. Well, just doing the principal values, first off, we'd get just pi over 3 plus 2 pi k. So principal value would be pi over 6 would be your final answer. Actually, pi over 3 would work as well, and that's a principal value. So in a problem like this, it probably is best to find all real values and then work from here to within one revolution, or to make sure you're in the correct range for principal values. So what we've done here again is we've taken what we've learned in our previous lessons. We learned some identities, the Pythagorean identities, the reciprocal identities, etc. We learned how to substitute those identities into other identities to verify those identities. And now we are taking those identities and substituting them and using our trig knowledge to solve equations that are reminiscent of what we solved back in our algebra days. So we've taken algebra and trigonometry and combined them into one problem, just like you're going to encounter in the calculus. So you've done it. Life is pretty good. You survived. And where? Oh, I stopped screen sharing. Something disappeared. Anyway, I can't figure that out right now. So that's enough for now. Have a great day.